Hi everyone, we're going to do a few quantum number examples, and these are of course posted as a handout. I think I'm actually going to do all the examples in one because it would be rather short. So I think I have three quantum number examples, and then what are the other ones? Oh, electron configurations, that's right. So just chapter 7 examples. They're kind of former test questions just to give you some practice, and they should help with the homework too. And so the first thing is, quantum number questions can be kind of difficult, right? Because it's abstract. You got these symbols, and we have to know that, it's just kind of memorizing. It's a lot easier to memorize things when there's some meaning attached to them. And so that's what I think may make this hard. Um, so one thing you can do on a test like that, and one thing that I miss is giving coaching advice, right? So I've tried to do this in some of the examples or sometimes when recording the content, but on a test with something like that, you can, when you get the test, or in this case, scratch paper, you can write down stuff, right? You can kind of do a knowledge dump and have it organized the way you're remembering it. And you know, maybe that doesn't seem to you like it should. Maybe I should add my face on this one, but anyway, like that should help that much, but it really does on the test because it frees up your brain to do some thinking. So when you start the quantum number ones, you might just want to go, well, what do I know about the quantum numbers? The first one is n, and its values can be the integer number scale, right? 1, 2, 3. And then the next number is L. The next quantum number is given the symbol L. And that starts at 0 and just counts up to n minus 1. And then the next quantum number is M sub L. And that is dependent. So each one is dependent upon the previous one, right? So the possible values of L are based on what value of n you have. You can go up to 0 to n minus 1. The value of m sub L is based on what value of L you're in. So m sub L can go from minus L to plus L. And so this, and then of course the spin can be up or down. But this question doesn't actually include the spin. All right, so here's the deal. That might be hard, I don't know if that's hard to remember or not. But if it is, write it on the scratch paper right when you get it, and that should help. There's another way too to help yourself with these, and that is to use that shell model. And you need to kind of have this for doing electron configurations, or it helps to do it for electron configurations. You can also do those with the periodic table method that I'll show in another video. But anyway, 1s, hopefully you've done enough, you will have at that point done enough of the homework that you know that it starts with 1s. And so the first shell has only one subshell. So you're done with the first shell. The second shell has two subshells, the S and the P. The third shell has three subshells, the S, the P, and the D. And it helps when you're memorizing this if you take my, hopefully this isn't offensive to you, but if you take my profanity way of remembering this, at least, when you're stressing out, maybe that'll bring a smile to your face. Anyway, so this filling order, right, remember putting the arrows on to do electron configurations, to do our filling order, it also has the pattern of the quantum numbers in it. All right, first shell, one subshell, second shell, two, third shell, three. See how that works? So that can help you with it as well. And then the other thing we have to know with quantum numbers that's a little different is that angular momentum quantum number, the L. Those values are numbers, but then for each number, you're given that letter. And obviously they're already here, right? That's the P, the D, and the F. So 1 is P, 2 is D, and 3 is the F. All right. So that's kind of a short refresher on quantum numbers. And then back to the question. Well, when you look at the question, you just look and see, are those values allowed? So when n equals 2, can L be 2? No, it can't. It can only be up to n minus 1, so 2 minus 1. So it can't be 2. So let's just X that one out. So that's not valid. Then n equals 0. Well, wait a second. We don't start the integer number scale at 0. The first shell is the first shell, not the 0th shell. So that's no good. Let's see. N equals 3. L equals 1. That's okay because it's, less than n minus 1. It could be up to 2. And then m sub L equals 2. Well, m sub L can't be 2 if L's only 1, right? That wouldn't work. And, if you remember where you're at here too, that L equals 1 is the P subshell. So this would be a 3P. If M sub L is 2, that means there's going to be 5 different. And we know there's only 3 in the 3P subshell. In any P subshell, there's only 3 orbitals. So that's, whether you remember it, quantum number rules, that goes minus L to plus L, or just that doesn't make sense, right? All right, so n equals 2, L equals 1, that's okay. M sub L equals minus 1, that seems okay. I don't see anything wrong with that one. So we'll tentatively circle that one. And then n equals 2, L equals 0, so that's the 2s, correct? But M sub L can't be minus 1. M sub L could only be 0. So that's not okay. So good, there's only one correct answer, which is how we like to have it on the test. All right, so that's the first one. And again, on all of these, really try to do them before you listen to my explanation. That's one thing I think we might be missing as a class, because when we do these, I wait, right? I ask you to talk to your neighbor and think about it. And so I try and do that in the video, but it doesn't work the same way, right? Anyway, so really try to think about them before you listen to the explanation. All right, so like I said, these are just old test questions, examples that I like to use. And this one's a straight memorization one. Which quantum number gives the shape of the orbital? So the principal quantum number, what does that give us? That gives us the size, right? Like the Bohr model, the size or the energy. Why am I still writing in red? Sorry. Magnetic quantum number. Now, it doesn't sound right, does it? Angular momentum quantum number. That's the L, right? And that gives us the shape. That's the one, S's are spherical, P's are the dumbbell shape, D's are all funky, right? So that's just, I don't want to say just, because I understand it's hard, but I do think that with hard work, the class can get 100% on a question like this. When this question's on the test, and maybe on this year's test, it's the size or energy of the orbital, and you have to answer principal quantum number, right? Could be any of these. So don't do the thing like, oh, never mind. I can't do that when we're not in person. I usually like to do the Princess Bride poisoning scene where I'm talking about, what question's going to be on the test. It's just I'm going to give you this one or that one. And is the poison in my... Anyway, never mind. It's a great movie. If you're stressed out, you should watch it. I just rewatched it with the kids earlier this fall. Anyway, next one. Again, answer it before I do. Which of the following is a set of quantum numbers for a d orbital? Well, that's definitely memorization, right? We already did that. L equals 0 is the S, 1 is P, 2 is the D. And so we just look through L equals 2 and find it. Excellent. Okay, so that would be the 3D orbitals. That's not too bad, is it? Let me take a little pause here and see if I can find the electronic configuration ones. And I think I've got them here. All right. Hopefully I have them in the same order. Oh, it looks like I got to back this out a little bit. Hopefully I have them in the same order that I posted them. But if not, if I can scramble them, hopefully you can work with that. So which of the following is the correct electron configuration for scandium? So remember, there's homework for electron configurations where you have to demonstrate mastery of writing electron configurations. So do those until you're 100% sure you'll get the electron configuration questions right on the test. So let me see. The way to do this is we've got to go to the periodic table, right? We got to know how many electrons scandium has. And I give you the symbol because I doubt that's one of the elements we had to know. So again, where's scandium? It's going to take me a while to find that one. I have no idea where it is. So I'm just like a student. I'm looking around and aha, there it is. And I don't know if that's even visible on there. But you have a periodic table. So it's element 21. All right, so we got 21 electrons. And we are not going to look down here at all, are we? All right, two ways to do this. One is with that. I should stop talking when I reach down to try and find the sheet I was going to show you. One is with, I just throw them on the floor because I don't have a big enough desk. So one is with this, right? That's how we can do it. Go through 1s, there's 2 electrons, 6 electrons, 2 electrons, 6 electrons, 2 electrons, 10 electrons, and just see how far you get, right? What if I were to show you, should I show you a different way than that? I think I will. I don't know if it's a good idea because I only have the periodic table that doesn't, I don't think, shows up very well. So here's scandium, right? So let's just go through the periodic table. First row is the first quantum number, principal quantum number, right? And in that shell, n equals 1, there's only one subshell, the 1s. That's why there's only 2 elements. Okay, so we'll fill that up. 1s2. Okay, and then we drop down to the second row, n equals 2. 2s, 2p. 1, 2, 3, 4, 5, 6. I don't have to remember it because I can't remember anything, right? 6. So I can go 2s2, 2p6. And now I'm at 10 electrons. Look at that. It says 10 electrons at neon. Not bad. We could put neon under here. We're up to neon. All right, what comes after that? Well, we drop down to element 11, third row. These are s electrons, so that's 3s, 3p. Well, that looks like it's going to work. 3s2, 3p6. Not bad. So we've filled up to 18. That's 18 electrons, isn't it? 10, 18. I think we're doing all right here. Okay. And we're just going to go in the periodic table until we get to our element. See how that works? That's not so bad. It's maybe easier than the filling diagram thing. Whichever works for you, though. A lot of students really like the filling diagram. And I've done that for many, many years. And so now we're back here, right? Element 19, 20. Those are s electrons. And we're in the fourth row. We don't even have to remember, right? So 4s2. Now here's where there's one thing you have to remember when doing it this way. There's a little disjunction, right? Because of the fact that we're going to do the 4s before the 3d. So this middle section, these 10 electrons, those are d's. But the third shell has 3 subshells. The 3s, the 3p, and the 3d. Okay? And so this next electron is in a 3d orbital, and so it's 3d1. All right? And so that's the correct electron configuration. And which one? Now, you got to look carefully, and this will drive you bonkers, because sometimes on a test bank question or a homework problem or whatever, they'll put them in different order, they'll skip one, whatever. So just check real carefully. Is this the right one? And does it add up to the right number of electrons? And I sure hope that that's the right one. I mean, the one thing you can do, let's say you're panicking, count the electrons and see if they gave us a couple that we can rule out because they don't add up to 21, or see if they put 8 electrons in a p subshell, right? I've seen that in homework or test bank questions as well. So we've got 4, 10, 18, 20, 21, and they're all in the same order that we did it. So that's the correct electron configuration. Now I should just, I don't know if I want to tell you this or not until you actually run into it. Some people will write this, and even though this is the way we fill it and the way the periodic table goes, they'll still go ahead and write the 3D in here. I'm not a fan of that, but I've seen it both ways. Which one's technically correct, I don't care, right? But I'm doing it this way. And so if you do see that, like if you Google things, you might find things different. Don't freak out. I kind of like just doing it, following through the periodic table, electron by electron, filling up that way. But I have seen it the other way. I just don't lose any sleep over it. There's plenty of things to lose sleep over, not that. All right, next question in electron configurations and this chapter. So how many valence electrons are present in a carbon atom? Now you remember the definition of valence electrons, right? So those are electrons in the outermost shell. And so the outermost shell, or the highest principal quantum number, right? But so we could go through and write the electron configuration for this and figure that out, but we don't have to, okay? We don't have to do that. What we're going to do instead is we're going to look where carbon is and see that's in group 4A. That means it has 4 valence electrons, okay? 1, 2, 3, 4. And that's the way to do it. There's no need to write the electron configuration for that. Okay. All right, take a minute and write the electron configuration for the sulfur anion. Pause the video. Okay, are you back? Did you really do it? You promised me you did it? Okay, so this one, how many electrons does it have? You got to be careful when you're given an ion. So sulfur atoms have 16. It's element 16. So it has 16, but it has a -2 charge. So that's +2. So it has 18 electrons. And in fact, remember how we talked about this a little bit. The reason that, I think I did in the orbital stuff, yeah, I'll do it again with periodic trends, but the reason that sulfur and oxygen and selenium, if it forms an ion, have a -2 charge in an ionic compound is adding 2 electrons gets them to the noble gas configuration that's particularly stable. You know, the filled S and P subshells that we talked, I think, yeah, I did. I talked about the octet rule. Anyway, so that's the idea. We're sitting at argon with 18 electrons. And so going through here, it's just this one. And you probably should go through and just write it either, you know, the filling order way or the using the periodic table way, but 1s2, 2s2, and hopefully you did do that before you came back. 2p6, so that's our 10, 12, 18. All right, and then I don't know what these distractors were, if that helps. You know, they're tricky distractors. And this one doesn't make any sense. This would have been sulfur without the charge, right? Without the 2 extra electrons. And it's never none of these on the test. Okay. You hopefully, I know you don't know me, but hopefully you know me at least better than that I would do that on a question like this. All right. Hopefully these examples will help you prepare for the chapter 7 part of the test, and hopefully with the homework as well. All right. Thanks, everyone.